Perfetto.
So, good afternoon to everyone. My name is Luca Moreschi, and I'm a researcher at the University of Genoa. And today, together with my colleague Erika Gagliano, we are going to discuss briefly the topic of life cycle assessment of food chain systems and the valorization of the related bioproducts towards circular economy. So, my goal for today will be to focus on the first section, so the life cycle assessment and its application specifically to the food chain systems and potential benefits arising from such kind of tools. And instead, my colleague will focus more deeply on the valorization of the byproducts. So just to start introducing the global context for the food production systems, we have one first main issue that it's the need, then the increasing need for feeding people all over the world. By the year 2050, the trends is showing that we should reach and overcome the 9 billion people living on the planet, and so the food security and food availability is more and more becoming a relevant issue to be dealt with. So this is why sustainable food systems are something to look for in the near future. We're considering all the pressures and the impacts that may come on the sectors of soil, water resources, but also mineral resources if we think about fertilizers and so on. In particular, we see how the agriculture sector is the largest consumer of worldwide freshwater resources, and you can understand quite easily why sustainability is a very important aspect for so not only the environmental one, which is the one on which we will focus today, but if we want sustainability in general, so social and economic sustainability. So focusing a little bit on general value of environmental impact, the most common environmental impact that you may have listened to is the global warming potential, or better called climate change in these days. So the overall emission of greenhouse gases to the atmosphere. We will see briefly how this kind of calculation are done. And for the European Union, we see how the agricultural sector contributes to around almost the 12% of the total global greenhouse gas emissions of the Union in the 2018. This percentage may change according to the different countries. So we see how it may range between the 41% almost for Ireland, till the lowest value is the 4.4% for Malta, and Italy, for the Italian context, it contributes to the 8.3% of the overall emissions still in the 2018. So it changes according to the actual relevance of the sector in each country, but we see how the contribution may be very relevant in some cases. Okay, so starting from this, we can understand how and why the definition of a standardized methodology for the assessment of environmental impact is something important to seek. This was done for the case of the life cycle assessment back in the 2006, thanks to the first ISO standards 14040 and 044, focusing on the general principles and guidelines of such kind of methodology. So we will see how today you will need most of the time different subsets of the documentation and guidelines for actually reaching in the end an LCA study. But the most general rules and guidelines comes from these two ISO standards, so international standards. According to what is written inside the standards, we can say that the life cycle assessment is divided into 4 different phases. The first one being the goal and scope definition phase. We will see in the next slides detail of each of these phases. The second step is the inventory analysis. This also is known as life cycle inventory, so as the LCI acronym. Then we have the life cycle impact assessment, so the LCIA phase. And in the end, we have the interpretation phase, which is not an actual phase contributing to the calculation and the management of data, but is most like an alert, remembering to us that we still have to check that everything comes together correctly in the end. And that's the impact assessment phase sticks to the goal and scope that we have defined in the first phase, and so on. So to start with the goal and scope definition, we can say that the goal is more about the general intention, the intended application of the study, and so why we are carrying out an LCA study. We may have different reasons. Of course, the common one is to try to assess the environmental impact of a system or of a process. Usually it applies to specific products, but it may also be applied to organizations. So this is the general application, we can say. But then we may need different subset of guidelines, as I was saying, if we want to use it for an internal use, or if we want to use it for external communication, and specifically if we want to match this external communication with some specific environmental labeling. So these are all things that have to be set in the beginning of the process to properly refer to the documentation needed. So this is more, it's some sort of a reasoning that we have to do. And then concerning the scope, we start to get a little bit more into some technical issues. So within the scope of the study, we have to define and analyze the product system that is going to be studied. We have to understand the functions of the system, and this mainly in order to set the functional unit, the system boundaries, and some other calculation procedures and assumption that may be needed sometimes for the lacking of data or for a proper management of data within the calculation. So this will be a brief introduction of LCA because you should have already started looking at LCA through the documentation sent previously to the state. But in the end, if you have any specific doubt, we will try to answer your questions. So just some concept that I want to check and to fix before going on. We know we have to refer our study to the functional unit, which is what defines the quantification of the identified functions of the product and of the system. This is usually coupled with the reference flow. Sometimes they may be measured in the same way, but the reference flow is actually the actual output of the product of the product system, and the functional unit is more about function. An example that I want to present to you is the one comparing two different systems for drying hands. So we have the hair dryer and the paper towel. We know that both systems are needed and are used for drying hands. So in this case, a functional unit that you may select is an identical number of pairs of hands dried. So it may be one pair on 1,000 pairs and so on. We can understand how this is actually a functional unit because it focuses on the function of the systems. But then our systems can be referred also to two separate reference flows. In the case of the paper towel, we may refer to the actual piece of paper towels that we need. And in the other case, we may refer to the time, to the electricity consumption, to the volume of hot hair that we need, and so on. So this is just to try to understand the difference between functional unit and reference flow. After that, another important step is the definition of the system boundaries that basically define all the unit processes that has to be included in the study to actually get to the point of obtaining as an output our reference flow. And from a more technical point of view, the system boundaries are defined as the boundaries that are crossed just by elementary flows and not by any other flows that may be materials or energy and so on. So just to better understand it, you will see the system boundaries is the light blue box, the external one. And you see that this is crossed by different arrows, which are actually elementary flows. And these are direct exchange of materials and energies with the biosphere. So this may be easy to understand concerning the emissions. So these are emissions to soil, water, and air. But when I talk about raw materials and energy as inputs, I'm actually referring to energy available in the biosphere. So maybe the kinetic energy in the wind, the chemical energy available in fossil fuels, and so on. And also in terms of raw materials, I'm referring to the availability of resources in the ground and so on. Okay, so but we're not talking about some processed materials. And after that, according to the extension and the dimension of the system boundaries, we may refer to different type of LCA studies, being the more extended one being the study from cradle to grave. So something that goes from the extraction of the raw materials till the end of life of the products. Then we have the from cradle to gate, which is usually a partial analysis, usually going from the extraction of raw materials till the production phase, and exclude, for example, the use phase. It may then also include the end of life, but it may change. And then a quite uncommon one, but still available, the from gate to gate study, which is usually focused just on the production phase. In the end, we can also say that we have a specific type of from cradle to grave studies that are called from cradle to cradle, and this is because of the total recovery and or recycling of the product at the end of life. So instead of ending up in a landfill or similarly, but in a sort of a grave, we call it from cradle to cradle. So this is concerning the goal and scope, the two main aspects of the goal and scope definition. We then talk about the life cycle inventory. So this is the step where we actually collect data from the primary data from companies and the stakeholders, and you have to then normalize all the data to the functional unit, to the reference flow, and start defining how to enter such kind of data, usually in the LCA softwares, where you can use not only primary data, but also secondary data coming from scientific studies, or better, coming from available databases. And in this step, we may also need to apply some kind of allocation procedures. This is basically the partitioning of the input and output of a process between the product system under study and one or more other product systems, which means that basically most of the time we will deal with systems having not one but two or more outputs. And so we may need to understand how to allocate the input and output among these sets of different outputs in terms of product. So the first rule suggested by the standards is to avoid the allocation, and this may be done by dividing the system into different sub-processes, which may allow us to actually split the system in separate sections. And so we may end up actually having a system with a single output. The other solution is to expand the system. So instead of focusing just on the aimed final product, we extend the analysis to the set of all the product outputs. But this is something that is not usually done because in some way it changes the actual goal of the study. So we may then allocate the input and output according to different relationship. The first one suggested is based on the physical relationships, but we can also refer to other kind of relationships, such as the economic value of the product or the energy content. Sometimes it may change according to the different systems that we are analyzing. After that, in the end, we go out. We come from the life cycle inventory, having as an output a list of elementary flows, describing our system boundaries and our whole system. And the life cycle impact assessment phase allows us to convert all these elementary flows into environmental impact that may be defined as midpoint or endpoint. Endpoint are less used, and you see they refer to three main sectors: the human health, the natural environment, and the natural resources. So this is actually an actual impact on the biosphere, but it's something that is not so largely used because we have some uncertainties in the conversion factor that may allow us to reach the endpoint. So usually we refer to the midpoint indicators. So they are potential environmental impact, but still we can define and evaluate this impact with a higher degree of certainty rather than the endpoint indicators. And so an example is the climate change I was presenting before, but you may have listened to acidification, eutrophication, land use, resource depletion, and so on. So we have many sets of characterization models available, each one having their own impact indicators and their own characterization methods. So the characterization methods are these sets of conversion factors that switch from the elementary flows to a single potential environmental, potential environmental impact, a midpoint indicator. This is done by going through two different steps. The first one is the classification. So we assign each of the elementary flows to each of the midpoint indicators in which they may have an effect. And then we apply the conversion factors, the characterization factors to obtain in the end a single value in an equivalent unit of measurement. So for example, all the greenhouse gases are characterized in terms of kilograms of carbon dioxide equivalent. So we refer to carbon dioxide as the main greenhouse gas. But each midpoint indicator has its own reference quantity, and after the characterization, we can end up having the total potential impact for each of the indicators selected. So this is for the LCA. But today we want to discuss how LCA can be applied to the food chain systems, and why it's important to assess and monitor the environmental impact coming from the agri-food systems. So a reason that may come to mind is that we need to reduce the impact of the systems. So we were saying, just concerning the global warming potential, we have a contribution of around 11% in the European Union, and this is why the EU launched the program Farm to Fork with different a set of different goals that are, for example, the reduction in the use of chemical pesticides by a reduction by 50% by the 2030. And this indeed has an impact, but also we have a great impact coming from the use of mineral fertilizers. And this may apply to different impact categories. For example, and we have a consumption of resources for the production of such kind of fertilizers. And specifically, in the last years, we've started to have a specific focus on the phosphorus, which is something that is being because phosphorus depletion is an issue, maybe an issue in the next future. And so this concerning the raw materials, but then the application of fertilizers can cause impact on, for example, the eutrophication, because we have the release of nutrients in the water bodies, but also the application of nitrogen fertilizers ends up creating the nitrous oxide or the nitrogen monoxide, according to the different nomenclature, which is one of the main greenhouse gas. So the emission of 1 kilogram of the nitrogen monoxide is equivalent to emitting 265 kilograms of carbon dioxide. And so this may be an issue, and this is why the Commission will try to act for the reduction of fertilizer use by at least 20%, but also the reduction of the nutrient losses. But then it also focuses on the antimicrobial resistance of linked to the use of antimicrobials, and also on the organic farming and all the benefits that may come to different guidelines and best practices for the agricultural production. How this can be done also from the perspective of the consumers. Well, for example, it can be done suggesting more healthy diets that can help both people and the environment. For example, we see that in 2016 and 17, 1 out of 5 deaths that happened in the European Union were attributable to the unhealthy diets. And so the change in the behavior of the population may help both people and the environment by the enhancing and the application of food labeling. And we will see some cases of food labeling. But also stepping up the fight against food waste, and Professor Gagliano will discuss more deeply this topic, and also trying to enhance the innovation and the promotion of a transition towards a more sustainable food systems. So going on briefly with, well, not so briefly maybe, but going on with the different kind of external communication solution of the LCA results, I would like to start with probably the most known one, which is the carbon footprint. This is defined according to the ISO standards, ISO standard 14067. So this is for the carbon footprint of products, but if you want to refer to the carbon footprint of organization, you have to refer to the ISO 14064. So take in mind that I will present environmental labeling focused on the products. Then, but we have some similar application with the water footprint. And then we start having some environmental product declaration that may focus on more than one impact category. Or apart from the LCA, we can still refer to more general sustainability reports that may be defined by guidelines such as the Global Reporting Initiative, and so on. But focusing a little bit more on environmental labeling for products and also on LCA-based labels, we can say that environmental labels can be divided in 3 different types. Type 1 is based on the ISO 14024, and so they are environmental labels and declaration that are generally not LCA based, but are verified by a third-party verifier. After that, we have the type 2, which sets, we have the ISO 14021, which sets the guidelines for the self-declared environmental claims. So these are not third-party verified, maybe LCA based, but it's not a mandatory solution. And then we have the type 3 labels that are third-party verified and are LCA based. An example of type 1 labels is the European Eco Label. So this started in the 1992. It's not LCA based, but it refers to a set of indicators concerning the environmental impact arising from the consumption of raw materials, energy consumption, and so on. And according to the different sectors to which you refer, this environmental label is given just to the top 5-10% of companies participating to demanding for the eco label. And so ho sentito una voce di sottofondo, ma forse è un microfono aperto per errore. Okay, so the idea is that if you see a product having the eco label on it, it means that it ranks as one of the best available product for that specific sector. After that, we discussed about we introduced the environmental product declarations, which are some types of type-free environmental labels. So these are LCA. These are based on the life cycle assessment methodology, and the idea for such kind of labels is to provide a third-party verified set of environmental impact for a product, so that the consumer may be helped in the identification of the best product for his proper needs. So in this case, the label is given to anyone applying to the system just after the verification of the study, and then it's up to the user, to the reader, to actually identify the best solution. This goes through different steps. It provides not only some environmental information, but also information about the company, the content of the product, and so on. Is based on on deeper guidelines, which are called product category rules, which sets for example, the functional unit, the system boundaries, some calculation procedures, and so on, to guarantee the comparability of different products applying to this specific labeling system. And in the end, it ends up having this kind of results. This is, for example, for carbon footprint, ecological footprint, and water footprint. But then, we have also the type 2 environmental labels, which are the self-made declaration, environmental claims. And so this just defines the reporting guidelines for such kind of claims. And this states, for example, that vague statements such as environmentally friendly should be avoided. But it's quite obvious if we think about it. But the environmental product declarations are not the only available type-free labels. We also have the product environmental footprint, which apply a quite similar system as for the EPDs, but this is governed by the JRC within the European Union. And starting from the PEF system in the more recent years, we also, the Italian scenario has also seen the introduction of the Made Green in Italy label, which couple the environmental assessment has for the PEF with the Made in Italy claim that one may want to state. Okay, so this was an introduction of the environmental labeling. I want to end up discussing briefly an application of LCA to the food sector. This refers to the scientific paper that we should have shared with you this summer. So this applies to the comparison of 3 different solutions for the production of high protein content food. So here in the bottom right corner, you have the dairy-based protein, then you have the lentil-based and the soy-based. And you see that these are compared in terms of actual protein content. So we have this line defining the farm gate price. And so we see that dairy-based should be the most economic one. But if you look at the climate change impact, we see how the lentil-based solution is the more environmental friendly. And this can be done because we refer in some way to the same functional unit. So we are defining the impact for per kilogram of protein. But you see that, for example, this was a review, and it also offered the data in terms of kilograms of carbon dioxide equivalent per kilograms of soybeans and per kilograms of soy meal. So this is not a protein content; it's just a kilogram of food. And from this, we may say that soybeans are better than is better than soy meal, but it's not actually the case because we are missing out the actual function of the food, and this is a problem specifically in the food sector because the scientific field, all the experts have not found till today an actual applicable solution for defining across all the different types of food products a single functional unit specifically describing the function of food, which is the one of giving us nutrients, energy, and so on. So, for example, if we look at the environmental labels, most of the time, but I would say also always, but I do not know all the available labeling systems. So most of the times you will have data refer to 1 kilogram of food product, but you see how this may limit an actual comparability between the systems. So this is why it's a longly discussed issue, one of the defining functional unit for the food sector. And we have different solutions proposed during the years, but none of them has been applied throughout all the labeling systems or through the scientific paper and LCA studies available. So this is an issue that may be overcome sometimes, focusing on the dietary pattern. So this is, for example, the comparison of different diets for an average day in the US. So they all refer to they all refer to a 200 kilocalories diet for one day, apart from the current adult in the US, which refer to the 2,150 kilocalories. And then you see that all of them should offer the needed nutrients for humans. So by this, you see that the land use is favorable for the vegan diet, but also the emission of greenhouse gases is way more favorable for the vegan diet rather than the unhealthy US diet or the Mediterranean diet. But then if we refer to the water use, we see how also the current adult diet and the vegetarian are quite similar to the impact for the vegan. And consider that this refers to this whole US scenario. So applying the same methodology to other countries or to other diets may change the results and may change also how the diets compare with each other. And so this may also limit for the understanding of the reader, because we may have a different scenario in which the vegan diet is better for the land use and the global warming potential, but it may be higher in terms of water use. I don't know, it may be the case sometimes. So the use of a longer list of impact categories increase the knowledge available for the reader and for the user, but limit the understanding of a non-expert user. So this is why it's also important to define coherent methodologies that may focus, that may end up having a single indicator as a result in order to offer something easier to read, because a lower value means a lower impact, and the opposite. And something that is we are trying to do across the scientific field is, for example, to focus on the water energy food nexus. So focus on indicators that may highlight the interconnection between these three main aspects. So food availability, water security, and energy security, sometimes also coupled with the climate issue or with the ecosystem issue and so on. So they may become water energy food climate nexus or water energy food ecosystem nexus. But the idea is to focus on such kind of interconnections, highlight them, and end up having a single water energy food nexus indicator that may help consumers and stakeholders and decision makers to set the strategies for a more sustainable agricultural system and food chain system. In the end, the last slide from my side, I just want to suggest you, if you want to look at it, this is the Suitable Life project. And I forgot to enter the website, but you will easily find it on Google by typing Suitable Life. And this project ended up obtaining a cookbook that allows for the selection of different dishes, also according to the different seasons. And you may choose, and you may understand also how this may be healthy for the diet, but also which may be the impact, in this case, just in terms of global warming potential, carbon footprint, and of water footprint, but which is the impact of a specific recipe. So it may help. The goal of the project was to help the consumer in setting a diet that may be both healthy and sustainable. Okay, so this is it for me. So I leave the stage to my colleague, and then we will end up having a session for the Q&A altogether.
Okay, thank you. Thank you everyone for participating. I just suggest a brief break, like 5 minutes, if it's possible, because I need to connect a screen. So if you want, you can stay. I just need 5 minutes. So just...
Va bene, facciamo 5 minuti di pausa, non c'è problema.
5 minutes, and also is the time for a coffee, but only 5. I am here,
Perfetto.
not for a coffee.
Perfetto, va bene, allora ci vediamo qua alle 14:25, tra poco.
Good afternoon to everyone. Good afternoon, everyone. I am Erika Gagliano, and I am a researcher at the University of Genoa. Thank you, of course, to my colleague, Luca Moreschi, that presented the life cycle assessment of food chain systems. This second part of this course will be focused on the valorization of related byproducts towards the circular economy. Of course, when we talk about the food systems, we refer to food system chain. Chain because normally are considered that like a linear process, wasteful, polluting, also depleting, because we are keeping natural resources for making food. In this sense, the food system are considered the primary driver of biodiversity loss, and also accounts for 30% of global GHG, greenhouse gases emissions. On the contrary, the circular economy framework is recognized as a solution for several problems, and in particular climate change and biodiversity loss. For this reason, the Ellen MacArthur Foundation, that is a UK-based charity, try to develop and promote the idea of a circular economy in order to tackle some of the biggest challenges of our time, in particular plastic pollutions or climate change and the loss of biodiversity. And starting from 2013, the Ellen MacArthur started to explore how the food waste, and in particular byproducts from food, could be used to help and to transform the food chain systems in more circular systems. For this reason, they started from 2021 this big project that is called the Circular Design for Food, in order to combine of food design with the principle of circular economy. In this sense, they make this infographic in order to collect all the main aspects of this circular design for food framework. And they suggest to think about the three main aspects when try to design and rethinking about the food systems. In particular, they talk about the designing product concept for nature. They talk about packaging, and of course, the last aspect is the ingredient selection and sourcing. The first goal for this circular design for food is to deliver positive outcomes for nature. So conduct several actions in order to have positive benefits for nature, doing several, of course, projects and actions. The second main topic is the packaging, because according to this framework and according to the scientific field, when design a product and consequently when make a product, you have to thinking on packaging in parallel. In order to avoid the strong implication of packaging on environmental outcomes. For this reason, also the packaging should be redesigned, of course, rethinking, in order to, and in particular, through three different stages, the strategies that are the elimination of course, of some packagings that could be avoided, reuse some materials, and also some material recirculation. Another aspect considered is the ingredient selection and sourcing. In particular, for this topic, the Ellen MacArthur Foundation try to have a collaborative approach, like an interdisciplinary approach between the research and development and also procurement teams, in order to have a jointly collaboration in order to make ingredient selection and also sourcing decision. For this reason, that is represented from the figure in the center of this main infographic, we can see which are the strategies according to this topic. We have the lower impact, the diverse, the upcycled, and also the regenerative produced. When we talk about lower impact, we are thinking about lower impact ingredients. This means the shift from the conventional produced animal products to lower impacts alternatives. And this also means the lower have also different from also rethinking about crops in order to have avoid higher impact crops and moving to lower impact crops. Another aspect is representing by the diverse ingredients. This means to increase the genetic diversity of crops and livestock, and therefore build food supply resilience. Another topic is represented again regarding upcycled, and in these cases, these topics means to have several actions, several projects, in order to have more opportunities and more technologies, in order to avoid to send or disposal food and byproducts to landfill, that is the last step, but also to turn and to obtain high value ingredients that could be also reused and recycled. Last point is represented by the regenerative produced ingredients. Since, as we will see also for the valorization of food waste, there is not one size fits all approach, but we need to think that some technologies and also some actions are site-specific. So we need to account and we need to consider also through the LCA in order to choose between different options. In this framework, of course, in this framework, another topics that is related to the valorization of waste, food waste, is given by the Agenda 2030, that is the Sustainable Development Goals. And in particular, the goal 12, that the main topic is ensure the sustainable consumption and production partners. This means to reduce the impacts, in particular for high-income countries, and a particular target that is related to the food chain is the target 12.3 that is giving a particular aim and a goal to reach by 2030, that is the halve per capita global food waste at the retail and consumer levels. So we are considering the consumer levels and also the retail, but also the reduce any food losses along production and supply chains, including the post-harvest losses. So in this target, we can consider the two different targets. One as related to the food waste at the retail and the consumer levels, but also reduce the food losses along production and supply chain. For this reason, the Agenda 2030, the Sustainable Development Goals, are considered two different indexes, like an indicators to monitoring the approaching and in order to evaluate if this target is reached. In particular, there are two different indexes, the food loss index and the food waste index. We started to consider the food loss index. In these cases, the food loss index measures the losses along the food supply chain, starting from the farm up to retail level. So in these cases, the pre-harvest losses, retail, and also the consumer waste are not included. So we are considering the first part of any kind of loss. And in particular, the food loss index that is calculated every year for different countries. And also in this graph, we can see the average, the global average represented by world. And in these cases, we have that the percentage, this index is calculated according to the percentage of food that is lost across the supply chain. And the 2015 is considered as the baseline. This means that when we look on this graph, values greater than 100 show increased food waste production since 2015, whereas lower values, lower than 100, indicate a decrease. And in particular, the food losses in these cases have been calculated considering 5 different groups: cereal and pulses, fruits and vegetables, fruits, animal production, and seafood. So in the information collected through this kind of index is related not only to country, but also according to the food category. The other index is represented by the food waste index. In these cases, this indicator measures the food waste at the retail and the consumer levels. So we have the amount of food waste produced by households and by food services. Consequently, with the food waste index, we are able to capture other food losses that are not considered in the previous one. And of course, the food waste index give other information related, for instance, to high income and low income countries, or developing or developed countries. For instance, according to this index and according to the last report that is dated on 2021, it is possible to consider that in developing countries, the biggest losses are represented about 40%, occur in the primary production. And this is due to an inefficiency of production systems. On the contrary, in developed countries, the majority of losses occurred at the retail and consumer level. And this, of course, represent the differences between developing countries and developed countries. We already mentioned that the difference between several categories, and in this graph we can see which are the global percentages of food waste produced by category. And we can see that the fruit and the vegetables represent about the 39–40%, like the global percentage, followed by cereals. This value should be also considered when design and when investigate the food waste valorization technique, because we need to move from the conversion of food waste to value-added products or energy. So according to the type of food waste, we need to consider the different valorization techniques. Indeed, when we considered the valorization of food waste, we have to think that an effective valorization of food waste undoubtedly would improve the sustainability of the whole food chains. And we can consider this hierarchy of food waste valorization that is represented in this graph. Moving from the up to the bottom part of this graph, we can look on the most preferred to the least preferred options. Since in the upper part, we can see that the prevention and the reduction are considered actions that could be preferred, since we are reducing from the origin the production of food waste. Consequently, we need to reduce the production of waste at the origin, and also this will have an effect on reducing also the production cost for food. Moreover, reducing the production of food will have several effects also on the food security and nutrition, and also will contribute to reduce the environmental impacts. Then we have another big category that are represented by the reuse of food waste. We already have some food waste, and the first option could be the reuse of this kind of food waste. The first option that is again most preferred is the reuse as a human consumption or as an ingredient in industrial uses. This should be prioritized, but in this sense, we need to consider also the human security. Another potential application of reuse could be the use of food waste as raw material for animal feed. The last three options are representing by production of energy, composting, and disposal. And we can see also that the sides of this shape represent also give an idea according to the best preferable and most suitable solution. Because when we consider the prevention and the reduction, we have the biggest one, and on the contrary, disposal represents the smallest one and also is the latest options. Since when we considered the production of energy, composting and disposal, we are approaching to some technology that could be also energy consuming. For instance, one of the potential application could be the anaerobic digestions. Normally is applied for organic waste, so not only food waste, but also municipal waste. And in these cases, he is becoming an attracting and effective valorization technique because we can obtain both resources and energy recovery. For instance, biogases, and after the upgrading of biogases, you can obtain biomethane. Landfilling and incineration are considering the disposal options, and both are identified as least preferable ones, because in particular in the cases of landfilling, we have also to considering the potential leachate, that is the liquid waste generating from a landfill, that need to be, of course, treated in order to remove any kind of pollutants. When we talk about incineration, and we will see how, we need to make also a distinction between also the thermal treatment that in some cases are considered equivalent. When we going in deep according to the food waste valorization, we need to consider that the first step in a valorization approach could be the pretreatment. Because when we talk about food waste, we need to distinguish between edible and inedible food waste. Since these two kinds of food waste have different physical and chemical characteristics. And in this case, we can apply different valorization techniques. For instance, when we have in this graph, we can see which are the potential pathways of the edible and inedible food waste. In particular, the green represents the edible part, and the yellow or orange represent the inedible part. And these are the pathway between the starting from the food production till the nutrients and energy recovery. Indeed, when we talk about the edible portion, normally it is reused also in the human consumption, followed by animal feed. So we have like an internal reuse. But when we talk about the inedible portion, depending of course on type of products, we can decide to reprocessing this kind of waste or send directly to the nutrients and energy recovery. Of course, the selection of food waste valorization technology mainly depends on the physical and chemical properties of food waste, in particular on the moisture content and again the composition of food waste. Indeed, the main goal of valorization techniques should be avoid energy, some energy intensive processes in producing value-added and use products for various applications. So we need to avoid have food waste valorization techniques that are energy intensive to obtain or to extract value added from food waste. And in particular, another difference between food waste categories could be animal-based food waste that is normally energy rich as compared to watery plant-based from waste such as fruits and vegetables. So we already mentioned which are the potential sources for food waste. We understand which are the pretreatment and the importance of pretreatment in order to separate the edible and inedible parts. And in these cases, we have different techniques like sorting, chipping, drying, or sorting. And also we can move from different stages in the valorization technique. As already mentioned, the main goal is to obtain energy or have other products that are value-added products from the food waste. But when we considered these valorization techniques, we need also to account any potential impacts in the economy, in the society, and of course in environment. As already mentioned from Professor Moreschi, in the food chain, we have to consider the several environmental impacts, but also in the food waste valorization, the environmental impacts mainly depend on the type of valorization methods selected. Indeed, when we selected a valorization technique, we need also to account that every recovery or recycling techniques should not imply any increase in the environmental impacts in comparison, of course, with the actual situation or the baseline. For this reason, also for the valorization phase, we need to consider each step of the valorization, and also we have to consider the input and the output of valorization processes, starting of course from the food waste in order to obtain products or energy. In order to account this input and output, and in particular in order to account the environmental impacts, and in order to design the best valorization option, we can refer to the life cycle assessment. We can use the life cycle assessment as a useful methodology that is standardized, as talked before, as standardized methodologies and a scientific approach to demonstrate the environmental benefits also of alternative options. In these cases, also, we can thinking that the LCA could be used as a decision-making support tool in order to highlight which are the environmental bottleneck of a specific process, and also to highlight also which are the potential improvements for a particular process. So, in general, when we considered the main relevant aspects in LCA study for food waste valorization, we have to consider the energy usage and the climate change, because when already mentioned, when we account for a processes, we need to transform the food waste into a new value added product with processes that are low energy consumption and making low greenhouse gases emission. Also, we need to consider the water use. In these cases, we need also to think that water use is an environmental critical point. Another aspect that often is overlooked is the use of toxic agents. For instance, there are some particular techniques aimed to extract some compounds, but in these cases, the extraction technologies use toxic agents. So normally it is referred to the green technologies that in order to avoid the use of these toxic agents. An example of a comparative LCA study is given in this slide. This is coming from a recent study and is also an example of a comparative LCA study. Since in this research, they compared 4 different options represented by landfilling, that is the existing treatment represented by scenario 0, anaerobic digestions, thermal treatment, and also the scenario 3 represented by co-processing the food waste with municipal not wastewater, there is a typos, municipal waste. Indeed, this study considered these 4 options in order to understand which are the options better in terms of environmental sustainability. So they considered 3 different impact categories that are climate change, human toxicity, and fossil depletion. And in this graph, they compared not only the 4 scenario, but also which are the steps inside the treatment. So they considered also the impacts coming from wastewater treatment, sludge treatment, waste treatment, transportation, and of course they considered the total impact referred to the particular impact categories. And according to this study, that of course is site specific because they referred a particular treatment and of course particular food waste, they obtained that the environmental performance of thermal treatment was the best option for most of the impact categories like climate change, human toxicity, and fossil depletion. Indeed, they obtained the lowest impacts. At the same time, the landfill option that is represented by scenario 0, and here is the red one, we can see that is the worst option because they obtained the highest value in terms of impacts. Moreover, the authors emphasize that the thermal treatment emerged as the best option because in these cases they effectively implemented the waste to energy measure. So they obtained the energy from waste, and consequently the effectiveness in energy generation was higher and giving environmental benefit. Similar LCA studies are ongoing in this project that is the National Research Center on Technology in Agriculture that is financed in the framework of Next Generation EU. In this project that is focused on technology in agriculture, these are the five, this is the mission divided in 5 main aspects that are the resilience, the low impact, so reducing the environmental impact, increase the circularity of agriculture system, increase the recovery, and also the promoting the safety in the agri-food chains. In particular, the University of Genova is one of the partners, and we are conducted several studies since the University of Genova are looking on byproducts generated from Liguria region. Other research groups are developing and optimizing the extraction techniques, and our group are conducting the LCA studies in order to understand the circular systems, in order to evaluate the circularity of these systems and also investigate the alternative solutions. The last 2 slides are, I have a problem with some sun, okay. I am moving, sorry. Okay, so according to this information provided during these lessons, me and also the Professor Moreschi would like to give you the last key message through 2 different indicators that could apply to everyone. So we already mentioned the carbon footprint, the water footprint, and also we mentioned the ecological footprint. We mentioned that is a tool able to measure how fast we can consume resources and generate waste compared to how fast nature can absorb our waste and generate new resources. This ecological footprint could be used to measure the Earth Overshoot Day. That is that represents a day that is calculated with this formula, but of course it is represented the day when the natural resources are when the natural resources have been already used. So if we consider that the ecological footprint is the measure of when is the measure of the resources consumed, and we considered, of course, the Earth biocapacity, we can consider the Earth overshoot day. And this is, of course, a date, and in 2023, this date was August 2nd. So it means that by August 2nd, we used more resources than that the Earth can produce naturally. So we are like in a deficit. And in particular, this overshoot day is also calculated for its countries. So using these two indicators, the Earth biocapacity and the human psychological footprint, we know which are the global overshoot day, but also the country overshoot days. Using these two information, we can discover our personal overshoot day. So we can calculate the ecological footprint of each one, and also we can have an idea how many planets we need for our life during 1 year. So I don't know if there are someone that could, of course, you can use both the link or the QR code, but we would like to have someone that could give us some information in order to make this calculation together. So we need like a voluntary. Raise your hand or just I don't know. And then after this calculation, we can go ahead with any Q&A questions. So just